Hello, grade 10s. In today's lesson, we are going to continue with the topic of electricity and magnetism, and we are starting on the section on electric circuits. Our objectives are to revise circuit symbols, to define current, to apply the formula for current, which is I equals Q over T, to define voltage, potential difference, EMF, and terminal potential difference, and to apply the formula for voltage, which is V equals E over Q. We will indicate the direction of conventional current in circuit diagrams. We will understand the difference between conventional current and real electron flow. We will learn how to connect an ammeter and a voltmeter to a circuit diagram. We will explain why batteries go flat. We will define resistance. We will apply the formula for resistance of R equals V over I. We will provide a microscopic description for resistance. So in other words, we'll understand resistance at a microscopic or at an atomic level. We will state the factors that affect the resistance of a given material. We will revise the rules of series circuits from grade 9. Series circuits are also known as voltage dividers, and we're going to apply those rules to circuit problems. And also from grade 9, we will revise the rules of parallel circuits. Parallel circuits are also known as current dividers, and we are going to apply those rules to circuit problems. There are several components in a circuit, and we need to be familiar with the circuit symbols of those components, and that involves connecting leads, a cell or a battery, a switch, a light bulb, which is a specific type of resistor, a general resistor, a variable resistor, a voltmeter, and an ammeter. Let's take a look at the circuit symbols in the table. The connecting lead or the connecting wire is just the conducting wire that connects all the circuit elements together. Current can only flow through the circuit if there is no break in the circuit. This conducting wire is often made of a good conducting material like aluminium or copper. Here we have a cell. Remember that a cell contains chemical potential energy that gets converted into electrical energy in a closed circuit. Now, a cell has a negative terminal, that's the shorter line here, and a positive terminal, which is the longer line. We always draw the negative terminal on the right-hand side and the positive terminal on the left-hand side, and together the positive and negative terminal make up one cell, which is known as one electrochemical unit, which we'll define shortly. Now, the difference between a cell and a battery is that a cell is a single electrochemical unit with one negative and one positive terminal, while a battery is made up of two or more cells that are connected together next to each other. And so if I have one cell here that's 5 volts, and over here I have 1, 2, 3 cells, if they're each 5 volts, then in total the voltage of this battery will be 15 volts. So here we have a battery made up of 3 cells because there are 3 negative terminals and 3 positive terminals. A closed switch, well, in the conducting wire we have to show 2 circles to indicate that we have a switch over here. This switch is closed, and over here we have an open switch, which creates a break in the circuit and it stops the flow of electric current. Now remember that a resistor, which we're going to learn about in more detail later, and we're going to define it later, a resistor is a circuit component that makes it difficult for the current to get through. So it provides resistance to the flow of current. And through providing that resistance, through making it so hard for the current to flow through, it forces the moving current, which is electrical energy, to be converted into other forms of energy. A circuit in and of itself without a resistor is completely useless, because it is useless to have electrons moving around and around in circles through a conducting wire. The whole idea of electricity is to move it through a resistor and to force that electrical energy to be converted into other forms of energy that are useful. A variable resistor, which we will discuss in more detail shortly, is a resistor that can be adjusted manually to change the amount of current that's flowing through the resistor. So, for example, in a dimmer light switch, as we turn that switch, we get light that's dimmer or brighter. So as we turn it, we actually change the amount of current that flows through that conducting wire. And so that changes the brightness of the light. The same applies to a volume control knob. So as we turn it, we control the resistance, which controls the amount of current that flows through the circuit, which controls the ultimate volume. A light bulb is a specific type of resistor. So a light bulb is a resistor that converts electrical energy into light and heat energy. The light energy is what we want to get out of the light bulb. The heat energy is actually wasted energy in the case of the light bulb. An ammeter is an instrument that we connect in our circuit in order to measure current. And an ammeter is always connected in series, and we'll see what that means in a moment. A voltmeter is an instrument that is used to measure voltage in an electric circuit. And a voltmeter is always connected in parallel in an electric circuit. And again, we'll see what that means in a moment. Let's start off by discussing current, then we'll move on to voltage, and finally we'll move on to resistance. So what is current? Current is defined as the rate of the flow of charge. Recall that electrons have a charge. Every electron has a charge of minus 1.6 times 10 to the minus 19 coulombs associated with it. Now, when those electrons are not moving, that's what we learned in the last section about electrostatics or static electricity. So when those electrons are not moving, they are just holding that charge, but they're static. However, when those electrons are moving, that moving charge is what creates an electrical current. Visually, current is how fast are the electrons moving through the conducting wire. That is why the definition is the rate of the flow, in other words, how fast, of charge, which is the moving electrons. If the electrons are moving faster, then more electrons pass a given point in a circuit in a second, making that rate of the flow of charge higher, making the current higher. And if the electrons are moving more slowly, that means that fewer electrons pass a given point in a circuit in a second. So that means that the rate of the flow of charge is lower, so the current is lower. Current may be calculated as I equals Q over T. And it is in this formula that we can find the definition. It is the rate of the flow of charge, where charge, Q, is the total charge carried by the electrons that are moving through the conducting wire. And remember that charge is measured in coulombs. T is the time that it takes the electrons to pass a certain point in a circuit. And we measure time in seconds. So remember that current is the rate of the flow of the charge. So when we talk about the rate of something, that means time. Current, which is represented by the letter I, is the rate of the flow of charge, and it is measured in a unit known as amperes. But what we need to realize is that an ampere is the same as a coulomb per second. We've just given it a different name. But remember that because charge is measured in coulombs, and here we have a division sign, so it's coulombs divided by time, which is measured in seconds. So it is coulombs per second. However, we don't call it that, even though it is not wrong. We call it an ampere. When current flows in a circuit, we show the direction of the flow of current by adding arrows to the circuit diagram. Now, what we know today is that current is made up of moving electrons, and we know that electrons are negatively charged. Now, what we also know today is that electrons leave the negative terminal of the cell. They repel each other in the negative terminal of the cell, and they move around the circuit to the positive terminal of the cell, to which they are attracted. So today we know that current is made up of negatively charged electrons that leave the negative terminal of the cell and enter the positive terminal of the cell. So we know that the real direction that electrons flow is from the negative terminal all the way around the circuit to the positive terminal of the cell. However, by convention, we say that charge flows from the positive terminal to the negative terminal. Now, yes, we know that this is wrong. We know that charge is made up of moving electrons, and we know that those electrons don't leave the positive terminal and enter the negative terminal. We know that that is the other way around. Where this comes from is Benjamin Franklin, who was a mathematician, scientist, and political figure in America in the 1700s. And he hypothesized that electric current is positively charged and it flows from the positive terminal to the negative terminal. Unfortunately, his guess was wrong. Now, let's just quickly recall that in the 1700s, he didn't know that electricity is carried by electrons which are negatively charged. Electrons were only discovered in the late 1800s. He did know that electricity was something that was moving through the conductors, but he didn't actually know what that something was. So Franklin made a 50-50 guess, and he guessed wrong in terms of the direction of electron flow. So why didn't we change the direction of conventional current once electrons were discovered? Well, that's because it was about 100 years later, and by the times electrons were discovered, the convention was already deeply established in terms of how it was taught and in terms of how textbooks were printed. And therefore, the scientific community decided to leave it as is, especially in light of the fact that the equations and laws of electricity still work regardless of current direction. Scientists discovered that electric current is the flow of negatively charged particles called electrons, like I mentioned, that happen in the late 1800s. And now we know that electrons move from the negative terminal of the cell or the battery or the power source to the positive terminal. And so that creates a flow in the opposite direction to Franklin's guess. As already mentioned, modern scientists decided not to change the convention, and to this day we follow conventional current direction. So if you're ever asked to show the direction of the current in a circuit, you must always follow conventional current unless stated otherwise. The instrument used to measure current is the ammeter. A galvanometer can also be used. A galvanometer is just like an ammeter, but it is an ammeter that is used to detect really, really small electric currents, like in milliamps or in microamps. The ammeter or the galvanometer must be connected in series with the circuit components. It doesn't work if it is connected in parallel. So what we mean by that is that the ammeter needs to be connected along the conducting wire. You'll see how that differs to the way that we connect a voltmeter in parallel. Now, it doesn't matter where you place your ammeter in the circuit, you would get the same reading regardless. Let's take a look at some examples. 45 coulombs of charge move past a point in a circuit in 2 seconds. What is the current in the circuit? We learned that I equals Q over T. The charge is 45 coulombs and the time is 2 seconds. So it is 45 divided by 2, which is 22.5 amperes. In a circuit, 95 electrons move past a fixed point in 1/10 of a second. What is the current in the circuit? Now, we know that I equals Q over T, but in this case, we were given the T, but we weren't given the Q. Instead of being given the Q, we were given the number of electrons. So can we work out the total charge based on those 95 electrons? Yes, we can. And the formula is Q equals N times QE. So that's 95 electrons times the charge of an electron. Now we know that electrons are negatively charged, so we know that this charge is actually negative 1.52 times 10 to the minus 17 coulombs. But because electric circuits deal with electrons that are moving, we don't take into account the fact that the charge is negative. We know that it is moving electrons, so it is always negative. Now that we have the charge, we may work out the current. So I equals Q over T. The current is 1.52 times 10 to the minus 17 coulombs. And the time was 1/10 of a second. And that gives us a current of 1.52 times 10 to the minus 16 amps. So in summary, current is represented by the letter I, and it is measured in a unit called amperes. And current is really measuring how fast are the electrons running through the circuit. That brings us to the end of current. In the next lesson, we will learn about voltage.